Welcome back again. So now let's talk about the different atomic forms of hydrogen. And first form we need to stay with nascent hydrogen. Nascent hydrogen. Nascent hydrogen. It is the hydrogen produced in contact with the substance to be reduced. Its sources are uh, first one. It is the metal and a protic solution. Metal plus a protic solution. Metal and a protic solution. Protic solution. So what is that? It is the hydrogen produced in contact with the uh, substance to be reduced. That is nascent. Nascent means the newborn. Okay, solution. And protic solution. For example, sing with acid, sing with any acid, or tin with acid, or sodium plus alcohol, or zinc copper couple with water or alcohol, or zinc mercury amalgam with HCl, and so on. These are the sources for the nascent hydrogen. We have heard of the nascent oxygen, nascent hydrogen, and such things. The source of nascent hydrogen is these things that is zinc with acids, tin with acid, or sodium with alcohol, or zinc copper coupled with water or alcohol, and zinc mercury amalgam with HCl. And also the other source are that was the metal with the protic solution. Now the next source is complex metal hydrates. Complex metal hydrates. Complex metal hydrates. And for example, lithium aluminum hydride is a complex hydrate, that is lithium aluminum hydrate, and sodium aluminum hydrate. They are all complex hydrates, and NaBH4 dibal H or dibal H. It is the diisobutyl aluminum hydrate. Diisobutyl butyl aluminum hydride. Okay, and so on. And the third source is the acidylated water by the by the process of electrolysis. We know that that nascent oxygens join to form the hydrogen gas in that process of electrolysis. However, practical existence of nascent hydrogen is not proven, and active nascent hydrogen. Okay, active nascent hydrogen is much more reactive because hydrogen at the moment of its formation is more reactive than the ordinary H2 gas. And for example, when ordinary hydrogen is passed through the acidic potassium permanganate solution or ferric chloride solution, neither of them is reduced, and that proves that. And however, when zinc pieces are added, both get reduced. Okay, and I can draw it here. I can schematically represent here. That is ordinary hydrogen. Ordinary hydrogen gives purple colored solution. Purple colored solution. Purple colored solution, that is KMnO4 of the KMnO4 or H2 with H2SO4, that is acidified, gives no change. Okay, ordinary hydrogen gives the purple colored KMnO4 or potassium permanganate solution, no change, no change in color, or acid reduction does not occur here. But if we apply some zinc pieces here, apply some zinc pieces, this zinc pieces with the dilute H2SO4, there is hydrogen is liberated, that is nascent hydrogen is here liberated, and decolorization occurs. Decolorization occurs. Decolorization occurs. That is liberated hydrogen reduces acidified KMnO4. Liberated hydrogen reduces the acidified KMnO4. It is believed that a part of energy liberated in the reaction producing hydrogen become associated with the hydrogen molecules and thus make them hyperactive. And the next form, it is the atomic hydrogen. Atomic hydrogen. First one is it was the nascent hydrogen. Now we are going to talk about the atomic hydrogen. Atomic hydrogen. When hydrogen is passed through an electric arc established between two tungsten filaments, hydrogen is dissociated into atoms. This form of hydrogen is known as atomic hydrogen. When the hydrogen is passed through the electric arc, which is established between the two tungsten filaments, the hydrogen is associated into the atomic form or atoms. And this type of hydrogen is called the atomic hydrogen. And we can show that it is hydrogen gas when passed through an electric arc. It is a reversible process. Okay, electric arc. Electric arc gives the atomic hydrogen. Okay, and the life period of atomic hydrogen is less, just the that is lifetime. That is lifetime for the atomic hydrogen is just zero point 0.3 seconds. That's zero point 0.3 seconds, and it readily returns to the ordinary form. And this conversion is highly exothermic and used for the welding purposes. The important reactions of the active hydrogen are the reaction with non-metals like sulfur, phosphorus, antimony, bismuth, etc. at room temperature to form hydrates, and hydrates with oxygen at very low temperature to form hydrogen peroxide, and however does not combine with nitrogen. And the second use is that, or the second reaction, the reaction with metals like lithium, sodium, calcium, etc. at room temperature to form hydrates, and it combines with metals like the silver and mercury at even very low temperature to form their hydrates. Even very low temperature means about minus 180 degrees Celsius. Okay, and I can show that reaction here. The silver reacts with hydrogen, active hydrogen, to give that hydrates, and at very low temperature, that is 180 degrees Celsius. 180 degrees Celsius. Also, mercury reacts with them to give hydrate. And the third one we need to note, it is more powerful reducing agent as it reduces oxides, chlorides, and sulfates of certain metals like copper, mercury, and silver, bismuth, and so on at ordinary temperatures, like copper sulfate, copper copper sulfate reacts with the active hydrogen to give H2S. It is reduced, okay, it is reduced to copper, and CuO also react with to give copper, that is reduced form, and also AgCl, the AgCl reacts with hydrogen to give Ag and HCl. And also it reduces CO2 and this carbon dioxide and carbon monoxide as CO2 plus hydrogen giving HCOOH, that is a formic acid. Here carbon dioxide forms reacts with hydrogen to form the formic acid, and also carbon monoxide reacts with or reduces hydrogen reduces carbon monoxide to formaldehyde, that is HCHO. And also it reduces P2O5 as it also reduces P2O5 as P2O5 reacts with hydrogen. Hydrogen reduces P2O5 to 2PH3, 2PH3 plus 5H2. So this is the reduced product. And it reduces alkali metal salts. It reduces also the alkali metal salts. Reduces alkali metal salts. Metal salts. For example, nitrates, nitrates, amides, amides, and cyanides, cyanides, two free metals, two free metals, as NaNO3. NaNO3 is a sodium nitrate is reduced to free metal, that is free sodium, Na plus HNO3, Na plus HNO3, and NaNH2 is reduced to sodium, forming ammonia. And NaCN or sodium cyanide, from sodium cyanide also hydrogen reduces it to the metal, that is sodium, and forms hydrogen cyanide. However, it does not affect the sulfates and halides of alkali metals. It does not affect the sulfates and halides of alkali metals. And the fourth one to be noted is that atomic hydrogen makes hydrogenation process more easier. Hydrogenation process more easier and at lower temperature than molecular hydrogen in organic compounds. Okay, and now we need to talk about the active hydrogen more detail. That is next form. It is active hydrogen. Active hydrogen. that is H3, not H or H2, it is H3. H3. When steam of H2 is subjected to silent electric discharge at ordinary temperature, active hydrogen is produced, and it is denoted by H3 and have a half-life of 1 by third of a second. It shows great chemical activity. For example, combines directly with lead and sulfur at ordinary temperature to form hydrates, and similarly it reduces copper or copper oxide to copper at ordinary temperature. So moving to the next portion about the water. Yes, the well-known substance that is water. Water everywhere. And water is very essential for the existence of life, and it constitutes about the three-fourth of Earth's surface and two-third of human body. And its high importance is because of its ability to dissolve large number of substances. And it's a good salt. It is known as universal solvent. Okay, and although it is most often perceived as a liquid at normal atmospheric pressure, water exists as a solid below 0 degrees Celsius and as a gas above 100 degrees Celsius. The term ice and steam are used to describe the solid and gaseous state of water, and water occurs in the following natural forms. That is the rainwater. Rainwater, rainwater. It is the purest. It is the purest of natural waters, and usually the first few showers of rain are not very pure, as it absorbs atmospheric gases. But afterwards, the rain water can be quite pure. And the second form, it is the seawater. Seawater. It is an impure water, and it contains about 3.5% of dissolved substance, out of which 2.5% of the seawater is sodium chloride, and this water is not fit for drinking purposes. And the third one, it is the surface water. Surface water. Surface water. Surface water, it includes streams, rivers, and lakes, and is most important source of water for all purposes. And it contains many soluble impurities, and near cities get contaminated with refuse and the sewage. The estimated world's water supply by oceans and land seas is 97.34%, and by polar ice and glaciers is 2.04, and by rivers is only 0.0001% of the total. Now we need to get the pure water from those impure water. How to purify the drinking water? So now we are talking about the purification of drinking water. Purification of drinking water. Purification of drinking water. Okay, and the purification of water needed for drinking purposes in towns and cities requires two major operations. The first one, it is removal of the suspended impurities, and second one, destroying the bacteria. Okay, destroying the bacteria. The removal of suspended materials is achieved by filtration through large filter beds made of layer of sands and gravel, and the addition of aluminum sulfate helps in the coagulation uh, colloidal particles. And there is a aluminum sulfate, like we can say that we know that alum which is used for the coagulation of the colloidal particles. So the impurities will be, or such sediments will be there at the bottom, and various methods are used for destroying bacteria such as aeration, chlorination, and ozonization, and so on. And that was the purification methods, and now we need to know the structure of the water. Structure of water. Structure of water. And H2O is a bent molecule in gas phase with a bond angle of 104.5 degrees Celsius and OH bond length of about 95.7 picometer, and it is highly polar due to the presence of highly electronegative atom like oxygen in it. Okay, and I can draw that. It is like oxygen at the center in the bend shape. The bonds are like this: hydrogen to hydrogen. Oxygen is bonded central. Oxygen is bonded to hydrogen in the bend shape, and the bond angle between them is about 104.5 degree in the gaseous state. Okay, the gas phase, 104.5 degree, and there is two lone pairs also like this. There are two lone pairs, and it is about 95.7 95.7 picometer bond length between oxygen and hydrogen. And H2O in its solid form, that is ice, is less dense than its liquid form, and due to which an ice cube can float on water. It is because in ice, each H2O molecule is surrounded by three H2O molecules in hexagonal honeycomb manner, and this arrangement gives rise to an open cage-like structure. There are evidently a number of holes or open spaces. In such a structure, lesser number of molecules are packed per milliliter. And when ice melts, a large number of hydrogen bonds are broken, and the molecules therefore move into the holes or open spaces and come closer to each other than they were in solid state, and this results sharp increase in the density. Thus, ice has lower density than water, and there is contraction in volume. The contraction continues from 0 degrees Celsius to 4 degrees Celsius as the hydrogen bonds are broken progressively. Thus, the density of our water is maximum at 4 degrees Celsius. That is the point to be noted. Density of the hydrogen or of the water is maximum at 4 degrees Celsius. That is the triple point of water. We know that. Okay. So now, what are the physical properties of water? We are talking about the physical properties. Okay, properties. And water is a colorless, volatile liquid with many unusual properties. Some of the physical properties of water and heavy water, that is D2O, I can show that the melting point, boiling point, as I can draw it as in a table. The first we are going to talk about the melting point property. You can write it down if you want, of the H2O and here of the D2O. Melting point, MP, melting point is about 273 Kelvin. Is 273 Kelvin for the water, and for D2 or the heavy water it is 276.8 Kelvin. And the boiling point, second one, it is the boiling point. Boiling point for water it is 373 Kelvin or 100 degrees Celsius, and for heavy water it is 374.4 Kelvin. And for the next property is the temperature of maximum density. Temperature of the of maximum density. Maximum density, that is 276.98. Water has the maximum density at 4 degrees Celsius, that is 276. 276.98 means 277. That is 4 degrees Celsius actually. And that of the heavy water is, it is 284.2 Kelvin. And the dielectric constant of water, dielectric constant, it is approximately that is it can be said that 80, but it is actually 78.39, and that of the heavy water it is 78.06. Okay, and due to its high dielectric constant and polar nature, water is an excellent solvent for polar and ionic substances. And the peculiar properties of water in its condense phase, that is liquid and solid, are due to the presence of extensive hydrogen bonding between water molecules, and some of these properties include abnormally high freezing point, boiling point, heat of vaporization, heat of fusion as compared to hydrates of other elements of same. Besides, high specific heat, thermal conductivity, and high capacity are properties which are responsible for making water a vital content of our life. And now about the chemical properties. Chemical properties of water. The first we need to know the nature of the water. What is nature? Nature. Water is neutral in nature with the pH about 7, and in pure water the concentration of the H plus ions is equal to the concentration of the OH minus ions. Okay, and that is approximately equal to 10 raised to minus 7. That is the reason for it becoming the neutral, that is pH about 7. And water undergoes self ionization, that is also called the autoprotolysis, that is self ionization, and hence it is amphoteric in nature. Amphoteric means it can act both as the acid and alkali. And the second property is that the decomposition. Water containing either alkali or acid when electrolyzed gets decomposed into hydrogen and oxygen, that is 2H2O. When it is electrolyzed gives hydrogen, 2H2, and oxygen. And when heated at about 2500 degrees Celsius, it breaks up into hydrogen and oxygen to a small extent, that is about 4%. About 4%. And now about the reaction with metals. Reaction with metals. It reacts with the active metals and evolves hydrogen. The reaction is highly exothermic in the case of alkali and alkaline earth metals, and the hydrogen evolved catch fire. It is again here, if the sodium reacts with water, it gives the sodium hydroxide along with hydrogen. Hydrogen can also catch fire. Okay, it is a really violent reaction and exothermic. And like also calcium reacts with water water to give calcium hydroxide and hydrogen. It is decomposed by it is decomposed by metals like zinc, magnesium, iron and such elements when steam is passed over hot metals, like reaction zinc plus H2O, zinc plus H2O giving zinc oxide plus hydrogen. So hydrogen is formed here. It's decomposed by the metals when steam is passed over hot metals. When this steam is passed over the hot metals, okay, and also of the iron with steam, they are really hot. These metals are heated to a very high temperature, and it also gives the hydrogen along with Fe3O4. Okay, and magnesium also reacts to give magnesium hydroxide and hydrogen. The lead and copper decompose water only at white heat. So this is so much temperature, and the gold, silver or gold or mercury and platinum metals do not decompose water. Okay, and now the next property is the reaction with non-metals. Reaction with non-metals. Reaction with non-metals. The fluorine decomposes the cold water. Okay, fluorine decomposes the cold water. I can show here. The like 2F2 decomposes the water to H2F2 H2F2 and O2 and or 3F2 plus 3H2O 3F2 plus 3H2O giving 3H2F2 plus O3, and this one is the ozonized oxygen. These types of oxygen formed is called or is known as ozonized oxygen. Okay, and chlorine decomposes the cold water. Chlorine also decomposes the cold water forming HCl and HClO. That is hyperchlorous acid. Okay, this Cl2 chlorine reacts with cold water, giving hydrogen chloride and hypochlorous acid. This hypochlorous acid. And however, in the presence of sunlight, only HCl is formed with the liberation of water. If the sunlight is present, we can get the hypochlorous acid. Only this reaction takes place. Light to store giving only in the presence of sunlight. Sunlight will give HCl and oxygen. Okay. Next reaction or the property is the hydrolysis. Hydrolysis. Many salts, especially the salts of strong bases with weak acids, uh, weak bases with strong acids, and weak bases with weak acids undergo hydrolysis with water. That is, I can show here. CH3COONA, which is a weak base, and with water it hydrolyzes to form weak acid like the acetic acid and sodium hydroxide. And the other reaction, that is CH3COONH4 reacts with water. It is a reversible reactions, and CH3 giving CH3COOH and NH4OH. NH4OH and FeSO4 plus 2H2O giving FeOH twice, FeOH twice, FeOH twice, and H2SO4. Here this salt is formed by the reaction of the weak acid with a strong base, and here this salt is formed by a weak acid with a weak base, and this one is formed by the weak bases with weak acid, and so on. Sorry, weak acid with the a strong acid. And however, salts of strong acid and strong base are not hydrolyzed with water. Some salts on hydrolysis of oxy compounds, that is BiCl3 plus water giving BiOCl plus 2HCl. That is, this is bismuth oxychloride. Bismuth oxychloride. That is BiCl3 reacts with the H2O giving BiOCl with the HCl, and also it's BCl, that is the tin chloride reacts with water. Sorry, it is antimony. Okay, sorry. And chloride of the antimony reacts with the H2O giving SbOCl and HCl. This is called the antimony oxychloride. Antimony oxychloride. Okay, and halides of nonmetals are decomposed by water. Halides of the nonmetals are decomposed by water. I can show that here. The PCl5 with water for H2O giving H3PO4 and HCl and PCl3 with water giving H3PO3 with 3HCl. SO2Cl2 with 2H2O giving H2SO4 plus HCl, and SiCl4 reacts with water giving H2SiO3 and HCl. And the next property is a reaction with hydrates. reaction with hydrates. Hydrates, carbides, nitrates, and phosphites. So let's talk about that. And water decomposes these compounds with the evolution of hydrogen, acetylene or methane, ammonia, phosphine gas, and respectively. And we can uh, CH2, that is calcium hydride, reacts with water to give calcium hydroxide. Calcium hydroxide with evolution of hydrogen. And calcium carbide, that is CaC2, reacts with water giving the calcium hydroxide along with the evolution of sorry with the formation of C2H2. Okay, and Al4C3 reacts with this carbide of aluminum, reacts with water to give 4AlOS thrice OS thrice plus methane. Okay, and Mg3N2 reacts with water to give 3 mgOH twice plus ammonia and that of the phosphate of the calcium, that is Ca3P2, reacts with water to give 3 CaOH twice and phosphine as the decomposes to give the methane. I have told that the hydrogen, evolution of hydrogen, acetylene here, or the methane and ammonia, phosphine, they are the evolution with respect to the hydrides, carbides, nitrites, and phosphites. Okay, and now the other property, that is the water in associated form. The association of water is essentially of five types, namely the coordinated water, or the water crystallization as found in the CuSO4 or the copper sulfate, aqueous copper sulfate. And the next one, it is hydrogen bonded water, hydrogen bonded water, hydrogen bonded water, and lattice water, zeolitic water, and clathrate water. Clathrate water. Okay, clathrate water. And zeolites have SiO4. Zeolites have SiO4 and AlO4. AlO4. This AlO4 tetrahedrons linked together in a three-dimensional open structure in which four or six-membered rings predominates. The open structure permits the formation of channels and cavities in which water and other smaller molecules like ammonia, carbon dioxide, ethyl alcohol, etc., can be trapped. That is the specialty of the zeolites. Zeolites. Okay, there are lots of spaces, and that is that of the clathrate clathrate there is a Latin word meaning from the clathratus. It means the enclosed or protected by crossbars or graftings. It's a substance in which one component, that is a host molecule, crystallizes with an open structure that contains holes or channels in which uh, atoms or molecules of appropriate size like H2O, NS3, CO2, there is carbon dioxide, or inert gases like and can be trapped easily. Now let's talk about the some tests for the water. Test for the water. Test for water. Test for water. The first one, it is a drop of water when added to anhydrous copper sulfate changes its color from white to blue. White to the blue. Okay, when the drops of water is added to the anhydrous, what is that? Blue. Okay, anhydrous copper sulfate, it becomes blue. It's blue vitriol. And the second test, water reacts with calcium carbide to evolve acetylene, which burns with bright flame. It reacts with the CaC2. That is a calcium carbide to give the acetylene flame, which it is a bright flame. Okay, and now those are the tests for water. And now we can move to some questions. It is a which of the following reaction involves hydration? It's actually a confusing question. All of them, how the reactions with the H2O, and the addition of water is called the hydration. Okay, now let's check all the reactions. First reaction is PbS plus H2O, which gives H2O2, which is a redox reaction taking place, and the product will be PbSO4 with water. There is no addition of water, and it's a redox reaction. It is a redox reaction. It's a redox reaction. And second one, it is a CaO, calcium oxide reacts with H2O, and it gives CaOS twice. CaOS twice, and this is a hydrolysis reaction. This is a hydrolysis reaction. Okay, hydrolysis. And now the next reaction, it is AlCl3 plus 6H2O. That will be giving AlOH OH OH twice, OH2 six times, having a charge of 3 plus 3 Cl minus. Here the addition of water takes place, and so this is a hydration reaction or the hydrogen reaction. hydration reaction. Okay, hydration reaction. And the next one, it is the Ca3 Ca3N2, that is the nitrate, reacts with water to give 3CaOH twice, C3CaOH twice plus 2NS3. This is also hydrolysis reaction. Hydrolysis reaction. Hydrolysis reaction. Among the given reactions, the water is added only with the AlCl3, so it is an example for the hydration reaction. So the option C is the right answer. And now moving to the next question. Give reasons lake freeze from top towards bottom. That's a good question. Why doesn't the lake freezes from the bottom to top? Why it freezes from top to bottom? Okay, the density of ice is less than that of the liquid water. During severe winter, the temperature of lake water keeps on decreasing, and since the cold water is heavier, therefore it moves towards bottom of the lake, and warm water of the bottom moves towards surface. This process continues, and the density of the water is maximum at 277 Kelvin. That is about 4 degrees Celsius. Therefore, any further decrease in temperature of the surface water will decrease the density. The temperature of surface water keeps on decreasing and ultimately it freezes. Thus, the ice layer at lower temperature floats over the water below it. And due to this, the freezing of water into ice takes place continuously from top towards bottom. Okay, and now it was 11 question from NCRT. And now, what do you mean by the hard and soft water? Hard and soft water. Soft water. Hard and soft water. Hard and soft water. So water can be hard. What can be hard or soft depending upon the nature of the substances dissolved in it. And hard water, on one hand, contains bicarbonates. Hard water contains bicarbonates. Hard water. Hard water contains bicarbonates. Bicarbonates, chlorides, 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 and sulfates of calcium and magnesium. Okay, and while the soft water contains or it doesn't contains, it is free from all such impurities, and in hard water soap does not lather as sodium stearate changes to corresponding calcium or magnesium salt, which precipitates out as in the reaction uh, 2C17H35 COONA, which is a soap, and when it reacts with hard water, there's the ions of magnesium and or the calcium, and giving the precipitate as C17H35 COO twice Ca with H plus 2Na plus. Okay, and soft water on the other hand readily lathers with the soap. The hardness of water may be temporary or permanent, and the temporary hardness is due to the presence of bicarbonates of calcium and magnesium, while the permanent hardness is due to the soluble sulfates and chlorides of calcium and magnesium. The former one can be removed by the, that is the permanent temporary hardness can be removed by simply the boiling Clark's process, and by those two processes, and the permanent hardness can be removed by the treatment with sodium carbonate using Kalkan process and using permutate or ion exchange method, ion exchange resins, and so many methods. So let's look at that. So first method for the removal of the soft hardness, the temporary hardness, is that by the boiling. Boiling Through boiling, the soluble bicarbonate changes to insoluble carbonates and gets precipitated as uh, the metal bicarbonates will gets precipitated by the heating or the boiling to the insoluble carbonates, metal carbonates, which are insoluble, and along with the soft water and evolution of the carbon dioxide. And here the M denotes the magnesium or the calcium. And the next one, it is the Clark's process. Second method to remove the temporary hardness is Clark's process. Clark's process. It is in this process the addition of calculated quantity of lime causes the precipitation of CaCO3, as I can show as the Ca HCO3 plus CaOH, which is the lime, CaOH twice, giving 2 CaCO3 plus H2O plus 2H2O. Okay, plus 2H2O, and MgHCO3 plus CaOH twice, giving 2 CaCO3 plus MgOH twice plus H2O. Okay, this is the Clark's process. And now these two processes are for the temporary hardness, and now we need to know the methods for removing the permanent hardness. That is first one, by treating with for the temporary, for the permanent hardness. Okay, permanent. Okay, I think you can see that permanent hardness. So first method, it is the by treatment with sodium carbonate, that is Na2CO3. That is Na2CO3. I can show that it is calcium sulfate, which goes by the permanent hardness, goes by the sulfates or the chlorides and sulfates. That is calcium sulfate can be removed by adding Na2CO3, that is the sodium carbonate, and giving CaCO3, which is insoluble carbonate, plus Na2SO4. And here the chlorides can be removed also by the same process, adding Na2CO3 or the sodium carbonate gives, this is also a reversible process, and we should remove that insoluble carbonates at that time it is produced, and MgCO3, which is insoluble, and 2NaCl. This is the first method, and second method is the Kalgan method. Second one, it is the Kalgan, using Kalgan. What is that? Kalgan is chemically sodium polymetaphosphate or sodium hexametaphosphate. The Ca2 plus and Mg2 plus ions present in hard water reacts with Kalgan to form soluble complexes. Symbolically I can represent here 2m2 plus, that is from the hard water, plus Na2Na4, that is the Calgon, Na4 PO3 6 times, PO3 6 times gives NaM2PO3 6 times plus 4Na plus. So this is the reaction, and the complexes so obtained do not cause hindrance in the lather formation. Okay, and the other process is the using permutate, permutate process, or otherwise it is called as ion exchange method. Ion exchange method. Okay, when hard water is treated with the permutate, also called the zeolite or hydrated sodium aluminum silicate, is I can show the formula Na2Al2Si2O8 Si2O8 XH2. This is the formula for zeolite or permutate or sodium, hydrated sodium aluminum silicate. The cations present in hard water are exchanged with Na plus ions here. That is Na2. I can show the general formula of sodium zeolite as Na2Z. Na2Z plus MCl2, that is a chloride, giving MZ plus NaCl plus 2NaCl. So in this process, the zeolite gets exhausted because of its conversion into calcium and magnesium salts, and when 10% NaCl solution is percolated through it, the exhausted resin gets regenerated. And, and the next method, it is the ion exchange method. Ion exchange resins. Ion exchange resins. Ion exchange resins. Ion exchange resins, and the ion exchange resins are the most popular water softeners these days, and the cation exchanger are granular insoluble organic acid resin having giant molecules with SO3H or COH group, and while the anion exchanger contains giant organic molecules with basic groups derived from the amines. And ion exchange resins remove all soluble minerals from water, and the hardness is first passed through a bed of cation exchanger, which removes the cations like Na plus, Mg2 plus, Ca2 plus, and others by exchanging with H plus ions. It is 2RH, which is a resin here. 2RH, that is a resin. 2RH resin reacts with Ca2 plus. This is the bed formed and gives R2 R2Ca plus, this R is resin, okay, R2Ca plus 2H plus 2H plus. The water coming from the cation exchanger is acidic on account of free H plus ions, and this water is then passed through another bed containing anion exchanger. This exchanger removes ions like Cl minus, SO4 2 minus, the sulfide ions, and nitrate ions at NO3 minus by exchanging with OH minus, it is hydroxide ions. Okay, and that reaction is RNH3 OH. This is a particular type of resin which reacts with chloride ion to give RNH3 Cl. Here exchange takes place. Okay, plus OH minus plus OH minus. This process gives distilled water and can be used in laboratories. Okay, the OH minus by the OH minus ion neutralizes the H plus. Okay, like H plus plus OH minus, giving H2O. This can be used as the distilled water. And the cation exchanger is regenerated by the action of an acid, and the anion exchanger is generated by using an alkali solution. And the disadvantages of the hard water are the hard water cannot be used for domestic purposes as it spoils the utensils luster and result in the scale formation and require a large amount of soap for boiler. And the second one, it cannot be used for boiler as it results in the formation of scales and bubbles corrodes the boiler surface. And and the third one, in industries like dyeing, printing, textiles, sugar, and so on, as plenty of water is required. Okay, and the degree, what is the degree of hardness? This point is degree of hardness. Okay, it is a measure of quantity of calcium or magnesium salts in a certain volume of water and is defined as the number of parts of mass of calcium carbonate equivalent to various calcium and magnesium salts present in million parts by mass of water. It is measured in parts per million or ppm. And so that was the degree of hardness, this amount of the calcium or magnesium salts present. And let's move to question. 1 liter of a water sample contains 1 milligram of calcium chloride and 1 milligram of magnesium chloride. The total hardness in terms of parts of calcium carbonate per 10 raised to 6 parts of water by mass is given here. So we have to find the answer to this question. We need to calculate the amount of the CaCO3 formed from 1 milligram of the CaCl2 and from 1 milligram of MgCl2. We know that 1 mole of CaCl2 is approximately equal to the 1 mole of MgCl2. MgCl2. So we can write as 111, that is 111 gram of CaCl2, that is the GMM CaCl2 is equal to approximately equal to 100 gram of CaCO3. CaCO3. So from this we can write as 1 milligram. We got the fraction here, and 1 milligram of CaCl2 will be approximately equal to 100 divided by 1111. Oh, sorry, 111 and of CaCO3. 111, that is 111, and that much of the milligram, and that is equal to approximately equal to 0.9 milligram of CaCO3. And in the case of the magnesium chloride, 1 mole of the magnesium chloride is also equal to the approximately equal to the 1 mole of the CaCO3. So we can write as 95 milligram or 95 gram of magnesium chloride, which is approximately equal to 100 gram of calcium carbonate. And from this we can write as 1 milligram of MgCl2 will be having approximately 10 by or 100 by 95 milligram of CaCO3, that is equal to 1.05 milligram of CaCO3. Okay, now we need to add them. Thus, in for the case of 1 liter, thus 1 liter sample contains equal to zero point 0.9 plus 1.05, that is equal to 1.95 milligram of CaCO3. That is called that it is said that so that is equal to 1.95 parts per million. So the answer is the 1.95 parts per. So option C is the right answer. So let's move to the next topic, that is the heavy water or deuterium oxide, D2O. The credit for the discovery of heavy water goes to the Urey, who first proved that ordinary water contains 1 part of heavy water in 6,000 parts of it. Lewis and Donald in 1933 were able to isolate few milliliters of pure D2O by continuous electrolysis of water containing alkali. And the preparation of the preparation of the D2 or heavy water. We need to know the heavy water is obtained mainly by the multi-stage electrolysis of ordinary water, as shown by the Washburn and Urey. It is also obtained by fractional distillation of ordinary water or by fractional freezing. And the physical properties are: heavy water is colorless, odorless, and tasteless mobile liquid, like that of the water, the ordinary water. And nearly all the physical constants are higher for heavy water than the corresponding values for ordinary water. And some chemical properties are: it gives all reactions that are given by the ordinary water but with a slower rate. This is called the isotopic effect. An example, for example, 2Na plus 2D2O, 2D2O, giving the same that of the ordinary water. That is, in the case of ordinary water, 2NaOH, but here it is 2NaOD plus D2, and the reactions are same as that of the ordinary water. And it also reacts with the number of compounds containing labile hydrogen atoms, and where hydrogen atom is partially or completely replaced by D atom, as NaOH plus D2O is a reversible reaction, and NaOD plus the hydrogen is replaced by the ordinary hydrogen is replaced by the deuterium plus HOD. Like that, HCl in aqueous state reacts with D2O, gives DCl plus HOD, and NH4Cl plus 4D2O, MD4 Cl plus 4HOD. And if the compound star contains ionic, this are polar hydrogen atoms, the exchange reaction takes place more readily in comparison to the compounds containing non-ionic hydrogen. And heavy water, like ordinary water, may be associated with salts as water of crystallization, giving deuterohydrate. For example, Na2SO4, Na2SO4 10D2O, and CuSO4 5D2O, MgSO4 7H2O, and so on. Okay, the biological and physiological effects also we need to consider that it has been established that heavy water of high concentration retards the growth of plants and animals. Pure heavy water kills small fishes, tadpoles, and mice when fed on with it. Taylor has shown that heavy water has germicide and bactericide properties. Water containing small quantity of D2O acts as a tonic and stimulates vegetable growth. Certain molds have been found to develop better in heavy water in comparison to ordinary. And to know more about the Cloudmender, visit our website. You can Google by typing Cloudmender Gaurish. Site appears as the first result, and or simply search Cloudmender and you will get the site as the third result. And also you can follow us on different social media platforms, and you can follow us on Instagram, and you can follow on WhatsApp. I have created a WhatsApp group for discussions on different doubts you have, and the links are given in the description box. Also a Telegram group for discussion and the same purpose, and a channel is also formed for giving off your learning steps, and all the links are given in the description box. You can check it later. You can also ask your doubts as comments in YouTube, and if you want more videos which would be uploaded in the coming days, please subscribe our channel and press that bell icon for getting notifications on time.
Hope you guys understood the topic. Thanks for watching my video. Always be free to ask questions. Subscribe to my channel for more videos. If you like this video, share it with your friends. See you guys.